I'd like to talk about distribution. Now, this is a math word, it's a math operation, but it really has to do more with stories than it has to do with rules. And I kind of want to show you what I mean by this. So let's look at a situation that maybe we've seen in an elementary algebra class, something like 5 times 1 plus 2, but we'll write it with parentheses outside. So we got 5 parentheses 1 plus 2, which we know means multiplication. So you can even think of this as having a little dot right here. And maybe some of us know the rule for what we're supposed to do for distribution, which means we're supposed to take the 5 and multiply it by the 1, and we're supposed to take the 5 and multiply it by the 2. But I want us to see if we can get away from this idea of rules and instead go into meaning. Let's go into story. So instead, let's think about what all of this means. This means that we have 5 of these groups of 1 and 2. So for example, let's take a look at that. So if I have 1 and 2 things, maybe I can represent that with these little dots. So I'll do a shaded in dot, and I'll do another shaded in dot, and another shaded in dot. And this will represent my 1 and 2 right here, my 1 and my 2. But I would like 5 of these 1 and 2s. Okay, sure enough. Let's look at that and say that I have another 1 and another 2, another 1 and another 2, another 1 and another 2, and another 1 and another 2. And so what are all the different ways that we can look at this entire thing? Well, we could look at this entire thing as saying I have 1 and 2 5 times, or we could look at this entire thing as saying I have 5 of these 1s, right? And I have 5 of these 2s. In other words, maybe we could look at this entire thing and say that here, if I counted up all these dots, I've got 10 dots, and here I've got 5 dots. So I've got 5 groups of 1 and 5 groups of 2, which together gets me 5 and 10, which together gets me 15. Or maybe I could look at all of this as 3s, and I could say that I have 3 here, and I have 5 groups of 3, 1 group of 3, 2 groups of 3, 3, 4, and 5 groups of 3. So I could look at this as 5 groups of 3. Or I could look at this entire thing as just counting up all the dots, which is that I have 15 total dots. So I could look at all this together and say I have 15 total dots. So all of these are equivalent statements. They're things that have the same meaning and just a different perspective. So when we talk about do we need to distribute in 5 times 1 plus 2, no, that's just one of the options we have. We could run it into the direction of distributing, where we look at this as 5 of each of these things individually. So that'd be 5 1s and 5 2s, which gets us 15. Or we could look at this entire thing as saying maybe instead we want to simplify within the parentheses. That would be 5 groups of 3, which would get us 15. Or we could look at this entire thing where maybe we try to express this still as groups, where maybe we try to do something like, I don't know, we could do we could rearrange these things. Like say I have 5 groups of 2 and 1. Maybe I now look at my picture from right to left and I say, here are my groups of 2, but then I'm going to think about and remember my groups of 1. That's still going to get me 15. So we have all these different equivalent perspectives, and this is what we talk about when we talk about distributing. It's just the way that we can take this group idea and affect it to everything that we have being repeated. So let's now take a look at this situation and let's replace it with something maybe a little bit more difficult. So maybe we've seen problems like this. 3 plus 4 times 2 plus 5. How would we handle a problem like this? Well, if we wanted to look at this more simply, we could maybe first say that I want to simplify the first set of parentheses, and I'll make that 7 of these 2 and 5s. Do we all see how we took the 3 plus 4 and turned into 7? So that means I have 7 groups of 2 and 5. So here's my 2, here's 5 more objects, and I'm going to repeat that 5 times. So that's going to be 2 times, and maybe I run out of patience, so I'll just say totally, that gets me 7 total groups of this. So there's 7 groups here happening of 2 and 5. Well, how much is that in total? That's going to be 2 groups of 7 or 7 groups of 2. Oh, so we can actually change the order of this entire thing and say that here we have 14, no matter how you look at it. And here we have 7 groups of 5 or 5 groups of 7. So that's going to be 35. So we have 14 and 35 gets us 49. But is this the only way we could look at it? No, we could look at it in through a completely different way. Maybe we know about foiling or distributing. That's the situation where we say, instead of taking the 7 and rippling it through, maybe instead we could have just taken the entire 3 plus 4 and rippled it through. We could ripple that to the 2 and ripple that to the 5, because now what we're saying is that I want 3 and 4 groups of 2 plus 5. Let's see where that appears in our picture. So that'd be 1, 2, 3, 4, 5, and our 2. Oh, there we go. There's a 2 and a 5, and then I could do that again. That'd be 2 groups of 2 and 5, and then I could have 3 groups of 3 and 5. Excellent. So it's 3 groups of 3 and 5, but I want 3 and 4 groups of 2 and 5. So that would mean I need 4 more groups of 2 and 5. Here's 1 more group of 2 and 5, 2 more groups of 2 and 5, 3 more groups of 2 and 5, and 4 more groups of 2 and 5. So notice what we've created is a little bit of this kind of area model, where what we're doing when we do 3 plus 4 times 2 plus 5 is we're talking about having 3 groups of 2 and 5, and then also having 4 groups of this 2 and 5. But in total, all we're doing is changing our perspective. We're not changing the meaning. So how much is that going to be in total? Well, the same 49 that we had before. But instead of looking at this as simplifying, we can now look at this through distributing. In other words, what we can think about is that maybe we'll express this entire thing as saying I have 3 and 4 groups of 2 and 3 and 4 groups of 5. Which maybe we can simplify from there and say that now I have 3 and 4 groups of 2. That would mean 3 groups of 2 and 4 groups of 2 and 3 groups of 5 and 4 groups of 5. Where what we're doing is just following that same pattern of distribution, but now we're going backwards. We're doing 2 as it multiplies into both the 3 and 4, and 5 as it multiplies into both 3 and 4. So it doesn't matter if the multiplication is happening afterwards or before. And where do we have this 3 times 2 and the 4 times 2 and the 3 times 5 and the 4 times 5? Well, my 3 times 2 are these dots right here. My 4 times 2 are these dots right here. My 3 times 5 are my 3 groups of 5, or my 5 groups of 3. Either way, those are these dots right here. And I have 4 times 5, which are these dots right here. So the important thing I like to bring up is that we're going to turn all of this into an area model to save us some of the confusion that normally comes around from trying to do distribution or double distribution. So from now on, what I'll probably be doing is if I'm looking at 3 plus 4 times something like 2 plus 5, I'll probably jump directly to this area model and say 3 plus 4 is really just saying I have 3 and 4 groups of 2 and 5. And I can even draw a little bit of a rectangle here because that's exactly what we have happening up here. If that's a surprise, then maybe think about it like this. All we're using is math, which is a model of logic, and we're choosing to model this multiplication through the lens of a rectangle. Because after all, the size of a rectangle is length times width. So if I call this whole thing my length and this whole thing a width, then multiplying it just becomes the size of that rectangle. Lots of creativity here. All right, 2 groups of 3 is just going to be 6, 2 groups of 4 is 8, 3 groups of 5 or 5 groups of 3 is 15, and 5 groups of 4 or 4 groups of 5 is 20. And again, we've just simply recreated this entire rectangle. Up here is our 6, this here is our 15, this down here is our 8, and this right here is our 20. So this is what it means to distribute. Distributing is nothing more than trying to pull out from an expression all the meaning that it has, that we have combinations of amounts and multiplication, which really just means groups. Let's look at a common problem that we have when we're working with distribution. Now, distribution, again, is just a fancy math word for saying we're multiplying something out. But I like to think of multiplying in terms of something visual, and I like to use rectangles. So imagine that we had the problem of saying something like x plus 3 times x minus 2. This is a difficult problem for people. But if we look at this through the lens of visuals or models, we'll actually be able to see this is a pretty easy problem to work with. After all, if I have multiplication, that just means I have groups of things. The problem being, of course, here that we just don't know how big x is, so we don't know how to make all of our groups That's not going to stop us though. So if we recall, what we're playing around with when we're multiplying is we could look at this entire thing through the lens of a rectangle, an area model. Because multiplying things, we can just treat as the length of a rectangle, and this is the width of a rectangle, and we'll draw a picture just like that. We're going to have one rectangle whose length is x plus 3 and whose width is going to be x minus 2. Well, how big would this rectangle be? Well, let's think through it. If I have x times x, that's going to be x groups of x. In other words, an unknown amount of unknowns. That feels a little bit odd. So let's try plugging in a number just to make things a little bit easier. Let's imagine that the x was 4. If x was 4, then 4 times 4 would just be 4 groups of 4, and we would get 16 dots out of that. 1 group of 4, 2 groups of 4, 3 groups of 4, and 4 groups of 4. So if I have x groups of x, what I'm going to be creating is just a square whose side length is unknown. In other words, an x square. So we've got x times x gets us x squared. In other words, x groups of x. What if I look at having 3 groups of x? Well, that would mean I have 3 of these x's. And so that's exactly what we get over on the right-hand side here. So we have 3 groups of x. If this feels confusing, think about x as a number. Think about it as 4. If you had 3 times 4, that would be 3 groups of 4, or 12. Here, we just need a placeholder, so we'll use x instead of making it simplify to a number. All right, what about x times negative 2? This means I have the opposite of 2 groups of x. In other words, we've got kind of a deficit. So we've got the negative 2 groups of x. And 3 times negative 2 means that I have the opposite of 2 groups of 3. That means I have the deficit of 3 groups of 2 or 2 groups of 3, which means I have negative 6. So all in all, we can actually multiply this out quite easily by saying we have x squared, 3x, negative 2x, and negative 6. Now, since 3x can be thought of as 3 of an amount, and negative 2x can be thought of as taking 2 of those amounts away, well, then that can simplify even more. X squared plus x minus 6. And this is how you can distribute from a multiplication statement into an addition statement. So this is the area model, and it allows for us to look at really, really difficult problems. Let's even take a look at a harder problem. The next one I want to look at is how would we multiply 8 times x times w times y, that's 3y, by 16z minus 5w. This is an incredibly intimidating problem, but if we see multiplication, we can always think of it in terms of a rectangle. So let's make our rectangle. It has a width of 8xwy plus 3y, and a height of 16z minus 5w. And let's just go through doing our full multiplication. 8 times 16 is going to get us 64. Sorry, much bigger than that. 80 plus 48, 128. There we go, 128. And then we have times x times w times y and times z. So x, w, y, z all being multiplied as well. 3y times 16z is going to get us, what, 3248 zy. 8xwy times negative 5w would be 8, and negative 5 gets me negative 40. X times w, which could just be written as w squared, times y. And then for the very last one, 3 times negative 5 gets us negative 15. W and y still need to be multiplied in. So if we want to do this full distribution, we can just go through and look at the size of our rectangle, which is 128 xwyz plus 48 zy minus 40 xw squared y minus 15 wy. Anything here we can simplify? Well, this is going to get us a number that's depending on x, w, y, and z. This is going to get us a number on z and y. This looks like it has 2 w's in it, and this one only has 1. So I think we have all of these being different terms. Not much we can do to simplify this beyond, so we'll box it and call it our expanded form. So this is the introduction into distribution. Distribution, or what's sometimes referred to as foiling, is nothing more than trying to recognize that we could describe a rectangle by the side length it has, like its length by its width, versus the size of the rectangle. And this happens plenty of times out in the real world as well. Like you could absolutely go to the store and buy a 2x4, or you could describe the sheet of wood you need by the amount of square feet it contains. This is the exact same idea. We're just changing our perspective without changing the meaning. Now, this being said, many people will have learned this through the name of foiling. So let's talk about what that means. FOIL is an acronym that just simply means first, outer, inner, and last. What this means is that if you get comfortable with a rectangle diagram, you can actually save yourself some time by recognizing that if you have a binomial, in other words, a length that is 2 terms wide, and a width that is 2 terms wide, you can do all of your multiplication in one line's worth of work. You just need to take the first 2 things and multiply them by each other, which would be 8 and 16. The outer 2 things, which would be this 8xwy and the negative 5w. The inner 2 terms, which would be these 2. And the last 2 terms, which would be these 2. Why does that work? For the same reason we have in the rectangle. If you multiply the first 2 terms, that got you this one, the next 2 terms got you this one, and then so on throughout the entire size. But why is it that I don't like foiling? Well, first of all, it's not a math thing. It's an acronym. It's a mnemonic. It helps us to do distribution quickly, but distribution is really what we're after. Also, people can get into trouble with foiling because it limits them to only having rectangles that are built up with 2 terms by 2 terms. Let me show you how instead, if we just get comfortable with the rectangle idea, you actually can do this for even more. Let's do something like 8x squared plus 2x minus 1 times x minus 3. Now, this is not technically foiling because you don't have only 4 things to multiply into first, outer, inner, last through, but we could represent this again as a rectangle. So let's do 8x squared plus 2x minus 1 times x minus 3. We're going to look at this through the lens of length times width in our rectangle, and we'll just multiply on through. X times 8x squared gets me 8x cubed. X times 2x gets me 2x times x, which is x squared. X times negative 1 would be the opposite of one group of x, which is just negative x. Negative 3 times 8x squared would be negative 24x squared. Negative 3 times 2x gets me negative 6x, and negative 3 times negative 1 gets me a positive 3. So what's another way of describing this rectangle, which has a length of 8x squared plus 2x minus 1 and a width of x minus 3? Well, I can describe it by how big the inside of it is. It's 8x cubed plus 2x squared minus x minus 24x squared minus 6x plus 3. In fact, if you look at this even more closely, what you'll recognize is that along these patterns here, you can even simplify this further. Because really what this is a rectangle that has 8x cubes. It has 2x squares and the opposite of 24x squares, which really just means that it comes down to 22x squares after you balance it out. And then you have negative 7x's and a 3. So I love to use the rectangle or the area model because I think it captures the idea of multiplication being just this groups that you're talking about, having this groups and the multiplication occurring through and being able to change your perspective, whether you want to look at the rectangle sideways or head on. But this is what I would say is probably a better and much more expandable model for your mathematics than to worry about trying to foil things in every situation.